Good morning to all of you. My name is Reinhard Scholtz and the title of my talk is the Battery Minerals Market. I work as Managing Director for Siebtechnik, a sister company of Multotech. After a market review in part 1 and the different raw material sources in part 2, my major focus is the third part. Here I will discuss typical lithium processing schemes and associated requirements for the applied technologies. These are crystallization, centrifuge separation, and drying. Prior to the big electrical vehicle boom back in 2017, 60% of the demand wasn't based on lithium batteries. This non-battery demand is expected to grow on a slow path only. Hence, the relative usage is expected to decrease to barely 30% in 2025. A similar development is projected for the battery lithium for consumer devices like laptops and phones. With a green agenda, electric vehicles and e-bikes, the dark and red portions are expected to be the growth drivers. EV will dominate demand in 2025 with a portion of at least 50%. Other sources forecast significantly larger portions. It's not just Tesla. Since 2020, more than 120 different electric car models are available. This picture from Bloomberg shows the available mileage range for some EV models bid by different car styles. All major car makers have announced to either completely switch to EVs or to at least offer a major part of their fleet as EVs in future. This slide shows further details about EV sales as main driver for battery minerals. What you basically see on all graphs is exponential growth. The left picture shows the actual situation. Globally, about 11.5 million electric vehicles have been sold till 2020. The green bar reflects the Chinese portion, which has ever since dominated the market and is actually at a total number of 5.3 million EVs in 2020. It also shows that the major growth, it's a light blue bar here, takes place in Europe. 90% of all EVs are passenger cars. The right pictures are about future expectations. According to Bloomberg, the number of EVs will increase by a factor of 5 to about 60 million EVs in 2025. The majority, with almost 90%, being passengers EVs, plus some e-buses, plus 2- and 3-wheelers, electrical, of course. Both diagrams refer to the expected future lithium demand expressed in LCE. LCE means liquid carbonate equivalents. 5.3 kilogram LCE equals 1 kilogram of lithium. Actual supply and demand is about 0.5 million tons of LCE. The chart on the left compares projections from different sources for both 2025 and 2030. For 2025, most projections see a demand of about 1 million ton LCE. The projection spread for 2030 is much wider, but in all cases exceeds 2 million tons LCE. The diagram on the right gives a more detailed overview of the expected global lithium supply and demand. The application demand is displayed by the sum of all bars. They add up to the already known 1 million ton here by 2025 and 2 million tons by 2030. Here too, passenger EVs, the blue bars, are likely to be the main driving force. The dotted gray line, demand implied by manufacturing, is an estimate derived from the total number of announced lithium battery cell manufacturing facilities, assuming 80% utilization. The black line is the nameplate capacity of all lithium plants actually in operation, construction, or detailed planning. And the red line, that's a so-called de-risked supply view, which assumes that lithium projects are often significantly delayed. According to this projection, lithium supply should cover demand until 2025, but a large supply gap is expected in the period thereafter until 2030. Following demand, Chinese producers like Tianji, Ganfeng, and Galaxy are also dominating the supply. The second largest supplier is SQM, followed by Albemarle and FMC. Next to the established lithium producers, there are a number of newcomers, which you can see on the slide, some of which have already invested in new production processes. Investment in additional projects is generally large, and since it can take up to 5 years to establish a production process, it is likely that not all planned projects are going to be realized. Following the importance of the battery mineral market, a large number of players are engaged as EPCs, engineering, and consulting companies, most of which are summarized on that slide. Various lithium projects have already been initiated since 2018, the majority of which are shown here, and our company is involved in projects indicated by the red dots. The 4 pictures show price increases for lithium carbonate, cobalt, nickel, and copper, all as of December last year. I selected this date on purpose as to avoid any interference with the Russian invasion in Ukraine and related supply chain problems. All prices have further increased since. As an example, lithium carbonate has more than doubled and is actually sold at $75 per kilo. As an intermediate summary, I'd like to make 5 statements about future lithium market expectations. The majority of all forecasts predict lithium demands for 2030 between 2 to 3 million tons LCE. Compared to today, this is about 5 times the demand. There are 2 main types of lithium-ion battery chemistry. NMC, that's nickel manganese cobalt, and LFP, that's lithium iron phosphate. NMC batteries have a higher energy density, so they allow for a larger EV range. They can be charged much quicker, and their efficiency is less influenced by cold temperatures. Against that, LFP batteries are safer, so they don't catch fire as easily as NMCs. They have a longer cycle life, and they don't need any cobalt. Lithium hydroxide is used for NMC batteries. LFP batteries are mainly made from lithium carbonate. Actually, there's a trend towards carbonate, especially in China. Due to efficiency reasons, however, battery chemistries are likely to evolve towards hydroxide over time. With many projects under construction or detailed planning, lithium supply should theoretically cover demand until 2025. A large supply gap is expected in the period until 2030. Why did I say theoretically? because more than 35% of the capacity additions will come from spodumene to hydroxide converters in Australia, and they have a history, unfortunately, of delayed startups. Only a relatively small portion of the nickel demand is used as battery material. This portion is projected to increase significantly, but that will increase global nickel demand only slightly. For battery use, pure class nickel 1 is required, the blue bar. Due to limited nickel sulfate deposits, future battery demand will likely be met by increased nickel sulfate production from lateritic deposits. Eliminating cobalt as battery material is not likely, except as I just expressed for the case of LFP batteries. Since these batteries do not require cobalt, future cobalt demand will heavily depend on future battery preferences. About 97% of the world's cobalt is produced as byproduct of nickel copper, most of it in the Democratic Republic of Congo. Supply of cobalt is strongly governed by copper and nickel prices. All today's lithium is either produced from brines or from hard rock ores. Clay deposits as lithium source are still in the development stage. Optimistic scenarios see clay covering maybe 10% of the total supply by 2030. Lithium is not a rare mineral. There are more than sufficient resources available globally. The problem is its low concentration of typically 1 to 3% lithium only. This means that per kilogram of lithium, approximately 98 to 99 kilograms of other salts or rocks need to be processed. A big effort. Brine is a source in South America. It is pumped to the ground and then water is evaporated in solar ponds. Prior to reaching a sufficient lithium concentration, many other salts will participate and will need to be processed and discharged, some of which are listed here. Pegmatites like spodumene are the other lithium source and are found, for instance, in Australia. The spodumene is grinded and concentrated prior to calcination at high pressures and temperatures. After calcination, lithium oxide can be leached with sulfuric acid and a lithium sulfate solution is produced. Both solutions here, lithium sulfate and lithium chloride, can be processed to either lithium carbonate or to lithium hydroxide. If lithium carbonate is wanted, the solution is neutralized with sodium carbonate, and sodium chloride or sodium sulfate are produced as waste salts, depending on the feed solution. For the lithium hydroxide production, caustic is used as neutralization agent. After waste salt separation here, both streams, the final lithium product is crystallized. Brine and hard rock-based processes are characterized by different pros and cons, which determine their overall profitabilities. Brines typically feature a higher capex, lower opex, and require years for ramp-up. Ponds need to be filled and get concentrated prior to being pumped to the next stage. That takes time. Against that, spodumene to hydroxide processes feature lower capital cost, higher operating expenses. There's not the soul as energy that costs nothing, and a fast ramp up. Economics of all projects are specific and cannot be judged in general. The faster time to market, however, can be seen as clear advantage for spodumene in this quickly changing market environment. Most spodumene hydroxide routes typically involve the following steps. In a first step, impurities like magnesium and calcium are separated by precipitation or ion exchange. Then there's a concentration process to almost reach solubility of lithium sulfate. The neutralization step features the addition of caustic to form lithium hydroxide. The sodium sulfate that's produced together with the lithium hydroxide is a waste salt and needs to be separated. Finally, lithium hydroxide is crystallized as monohydrate, separated and dried. Overall, design requirements for this process are challenging. A high lithium yield and at the same time ultra-pure lithium product needs to be achieved. In addition, no metal pickup in the lithium product is allowed, and in case of lithium hydroxide production, any contact with CO2 must be avoided. Such contact would immediately result in the formation of lithium carbonate. These two design requirements here can best be met by crystallization. In the following, I'll do a quick wrap-up of the fundamentals of this crystallization process to better understand specific needs for battery minerals. Finally, I will then describe the 4 process steps after neutralization in some more detail. Supersaturation, expressed as delta C in both graphs, is the driving force for each crystallization process, and its proper handling is of paramount importance. Supersaturation can be generated by various means. Common are a solvent, withdrawal, or lowering of the temperature. In case of a strong temperature dependency of the solubility curve, the cooling method can be chosen. This process is always energetically preferred. Examples are Glauber salt, nickel sulfate, hexahydrate, and copper sulfate heptahydrate. For systems where the solubility does not or only slightly depend on temperature, evaporation must be chosen. With these flat solubility curves, massive cooling steps would be required in order to produce only small supersaturations. Evaporative crystallization is typically applied, here it's shown for lithium hydroxide, sodium chloride, or sodium sulfate. The greater the supersaturation delta C is chosen, the faster the crystal grows. It's a blue line here, and thus the smaller and cheaper the crystallizer. However, the supersaturation cannot be set arbitrarily high, since the nucleation process also depends on it. There are 2 forms of nucleation: spontaneous primary nucleation and the secondary nucleation. Primary nucleation, the red line here, occurs when a critical supersaturation level is reached and must be avoided by all means. Otherwise, billions of smallest nuclei would form instantly. Against that, the secondary nucleation, the green line, is required in order to produce new nuclei that can further grow inside the crystallizer and compensate for the offtake of crystals from the process. Each crystallizer must operate within the so-called metastable region. Proper crystallizer design is all about balancing nucleation and crystal growth. High product purities can only be achieved with sufficiently large crystals. These are easier to separate and wash. This slide attempts for a graphical explanation of how nucleation impacts the achievable crystal size. Here, the supersaturation reflects the desired product purity. Following this example with a production quantity of 10 grams, 10 nuclei will produce 10 crystals with a mass of 1 gram each. If, on the other hand, 10,000 nuclei are initially present, These will grow under the same process condition towards 10,000 product crystals of only 1 milligram each, so very small. Therefore, if a coarse product is desired, as in the present case, the nucleation rate must be limited. This slide shows how to generate and control supersaturation in a vacuum cooling crystallization process. On the right, you see a FC crystallizer with an outside recirculation pipe and a recirculation pump. This keeps crystals in suspension, and the flow also serves to adjust the degree of supersaturation created here and distribute it evenly within the crystallizer. On the left, a solubility curve diagram is shown. The red line marks the solubility curve. The metastable zone extends till the dashed line, where spontaneous nucleation will occur. The suspension inside the crystallizer, 0.3, is mixed with feed, 0.1, to form 0.2. In vacuum cooling crystallization, this feed is more concentrated and at a higher temperature than the mother liquor, and the mixture forms 0.2. This mixture is then further conveyed to the vapor liquid surface, to the evaporation chamber by the circulation pump. At this surface, the solution expands adiabatically to its saturation vapor pressure. Here, 0.4 is reached. The required vacuum is generated by this condensation system. Here, a cooling, barometric cooling vessel is shown, and by a vacuum pump for discharge of the non-condensable gases. The diagram process is shown here. That's a line 2 to 4, where the solution is simultaneously cooled and concentrated by the water removal, as represented by this line 2, 4. Finally, the generated supersaturation is released on the suspended crystals by crystal growth to reach this 0.3 here. And yeah, this closes the cycle. Coarser crystals are easier to separate and wash, and hence a classifying withdrawal of the solids is an important feature of a crystallization process when aiming for ultra-high product purities. On this slide, you see exactly the same crystallization process as on the previous one, except that the feed isn't introduced here at this point, but it's introduced via a washing signal at this point. This device uses the fact that the settling velocity of an individual crystal depends on its size. That can be seen here in this enlarged view of a detail from inside the washing signal. With a certain constant upstream velocity of the liquid, there's just one crystal size where the settling velocity is identical. The settling velocity is identical to the upstream velocity of the liquid. That's this particle here in the middle, and its size is called the cutoff size. Smaller dust particles are settling slower and thus trapped into the liquid stream and are recycled here with the overflow back to the crystallizer. There they are given additional time to grow. Only really the rock crystals, they can settle against the upstream liquid and will find their way towards the centrifuge. Sodium sulfate that's formed during neutralization must be separated. To maximize process efficiency, the sodium content added to the final lithium crystallization here must be as low as possible. In the equilibrium diagram, you can see that low sodium sulfate concentration can be achieved here on the left side in the area of the Glauber salt. Standard vacuum cooling processes can reach sodium sulfate concentration of as low as 6%. In this application, the effort of an additional surface cooling process is justified. At sub-zero temperatures, concentrations of about 3 weight% are reached. At these low temperature, the viscosity is high and the rather small crystals are formed. Since small crystals pass through the filter screen of the centrifuge, a polishing filter is additionally required. This filter prevents solid sodium sulfate from entering the final lithium purification section here. Since the upstream effort to extract lithium is so enormous, no lithium should be lost with the Glauber salt. Therefore, this waste salt is melted by heating and further addition of water and then crystallized a second time at higher temperatures as sodium sulfate. It is then separated by a pusher centrifuge and dried. As explained, a proper process design and control of supersaturation is paramount to create large crystals. The first crystallizer here is equipped with a washing thickener or alliteration lag for first selectively discharging only large crystals, increasing of the slurry density in front of the centrifuge, and washing of the crystals by displacing mother liquor from the first stage with purer liquid from this second stage here. To achieve battery-grade lithium hydride purities, the lithium hydroxide is dissolved in water and crystallized another time and washed as to achieve those very high purities. For lithium hydroxide separation, pusher centrifuges are used. That's because they offer long retention times for the solids, low loss of solids in the filtrate, low crystal breakage, and most importantly, they allow for intensive washing of the filter cake. Pusher centrifuges are horizontal basket centrifuges. They have filtration bowls, which are equipped with metal screening plates or slotted sieves. Feed suspension enters the centrifuge continuously via this feed pipe. A distributor gently accelerates and distributes the suspension evenly over the entire periphery of the sieves in this filling area. The greatest part, already 80% of the mother liquor, is already filtered out in this feed stone and a stable cake is formed. Along with the rotary movement of this first basket, there's also an oscillating axial pushing motion to transport the cake out of the bowls. Since washing is essential, a second a two-stage centrifuge with a second conical screen is used. The wash liquid is applied continuously over the cake via several adjustable wash nozzles. On the conical basket here, G-forces increase and at the same time cake height decrease with increasing screen diameter. Lower cake heights are easier to wash. In addition, the cake is broken up and rebuilt at the transition point of the first to the second stage. All this helps to eliminate potential mother liquor inclusions in the cake. The washed product leaves the centrifuge via the racetrack and the solid housing. For this application, typically wedge wire screens are used. They are available in various profiles, various wire thicknesses B, and of course for the individual application in various slot widths. Selecting the right configuration requires application knowledge and is key to an optimal performance of the centrifuge. In some applications, very small particles are formed. This happens frequently with lithium carbonate. These small particles would no longer form a filter cake in filter centrifuges. In these cases, discontinuous peeler centrifuges are typically applied. There are two types, horizontal on the left and vertical on the right. They are both equipped with a filter cloth, which is placed on a perforated basket. The operation cycle for both types is quite similar. In a vertical peel, the suspension enters via this feed vertically, in the horizontal peeler horizontally. Under the influence of centrifugal force, liquid filters through the filter cloths and through the holes of the baskets. Even fine solid particles are retained by the filter cloths, unlike the pusher. Cake thickness is controlled by a mechanical pedal detector. It stops the loading phase once the desired cake thickness is reached. For washing, there's no difference between the two types. The washing liquid is dispensed over the solid product along the entire length of the basket. The wash liquid passes through the product and then further through the filter cloth and the holes of the basket. It replaces retained mother liquor in the cake by pure wash liquid. Only upon completion of the washing phase, the centrifuges in both cases is accelerated to its maximum speed. It's maintained for a given time to achieve the final residual moisture. Discharge is effected by means of a scraping knife in the vertical peeler at reduced speed. Like a cheese slicer, the knife is gradually moving towards the outside, thereby cutting a major part of the cake. In the vertical peeler, cake discharges by simple gravity through this discharge chute. In the horizontal peeler here, the product is collected in the center chute and then discharged by a screw gun. As just shown, it's easier to fill and build the cake homogeneously on the horizontal peeler. During operation, the cake is subject only to rotational force. This force pushes the cake towards the basket. A uniform distribution of the cake on the vertical peeler is obviously more difficult. Here, the height of the cake itself also exerts an additional vertical force. This results in higher risk of unbalance for the vertical machine. From a mechanical point of view, the vertical peeler is superior as it is subjected to much lower forces. They are therefore the less expensive alternative and should be used if their performance is acceptable. Horizontal peelers offer a better and more robust performance, but require heavier constructions. They are the more expensive alternative. I hope I haven't confused you with the peeler explanations, since they are not required for lithium hydroxide production. Product crystal size determines the selection of the most suitable separation device. Pusher and screen warm centrifuges are the workhorses of solid liquid separation and the most economical choice for products from about 100 microns up to millimeters. Peelers or decanters are used for cases where lithium carbonate or other salts crystallize at D50 of about 20 to 50 microns. This slide shows a typical configuration of a fluid bed dryer. A screw conveyor is used, usually installed between the centrifuge and the inlet of a dryer leading upwards to prevent centrifuge wash from entering the dryer. Air intake is here on the left side of the slide. Part of the air is heated for drying purposes, in this case by direct gas-fired air heating. The air enters the drying chamber from below. The remainder of the air, not heated, is used for cooling in the second part of the dryer. Due to the high airflow, fine particles up to at least 100 microns will be taken off in the dryer body together with the air. They must be captured together. This is typically done in a cyclone for removal of most of the dust. The fines at the underflow of the cyclone are as dry as the main dryer product, which means they are frequently blended back into such product. Prior to being released to the ambient, the air still has to undergo further treatment that can be in wet scrubbers, as in the present case, or in bag filters. This photo on the left shows the inside of the drying chamber. Why do I show it? Because you can't see anything. There's virtually nothing that could hinder the free flow of the crystal bed. The short video shows the forward moving action of the bed. We're working with a high amplitude and low frequency. Adjustment can be done by selecting different rubber buffers. In order to avoid direct contact with CO2 from the air, the CO2 can be removed from the air or other gas media can be used. In most cases, however, a closed-loop drying process is applied. This process is explained on the left here, the simplified PNID. On the right, the same process is depicted in an HX diagram. I'm starting here with point 1, the coldest point in the process. Here in the diagram. The airflow is heated, the heater, at constant moisture level to a temperature of, for instance, 60 degrees, 2.3. The heated air can now absorb the moisture from the fluidized bed. The higher the temperature becomes, the larger this drying potential delta X becomes. If we would increase temperature to here, the delta X would be much larger. After the normal air treatment to get rid of the dust here, which I just explained, the air is cooled to 20 degrees by means of chilled water. It's from here to here. Since air at 20 degrees C can only absorb much less humidity than the hot air at 60 degrees, the remainder is released as water and discharged from the process. When point 1 is reached here, from here, the air circuit is closed again. Lithium carbonate drying is either lithium hydroxide in two aspects. An open loop drying process can be applied, as shown in this slide, and also drying temperatures can be higher since there's no risk of dehydration. Other battery minerals that are dried in a fluidized bed dryer are, for instance, copper sulfate heptahydrate and nickel sulfate hexahydrate. As to avoid dehydration, these applications also comprise low temperature drying between 50 and 80 degrees. Calcining is also possible by means of high air temperature. On the left photo, you see again the centrifuge, an upward carrying screw conveyor, and the product inlet into the dryer, and here the air inlet into the dryer. As a summary, battery minerals demand is driven by EVs. In 2030, demand for most battery minerals is expected to be 5 times as high as today. Substitution for lithium as battery mineral is highly unlikely. The use of lithium as hydroxide or carbonate depends on the battery chemistry and is likely to evolve towards hydroxide over time. Processing technology is well developed, since each player or investor wants to own its own IP rights, the process is slightly adjusted each time. And application knowledge is important in this application. At the end of my talk, I want to express my gratitude, first to Multitech for inviting me for this keynote presentation, and second to all internal colleagues, especially the graphic designers that helped me in the completion of this presentation. Thank you for your attention.